Hey, what's going on, guys? CMK here. So in the previous video we already learned how to load programs into CMK computer and how to input a program using machine codes via the 4x4 keys keypad. And now it's time to write our very first program to run on this computer, basically. And I'm going to be using what I call CMK assembly language. So literally the mnemonics that allow to translate this assembly instructions to machine codes that CMK computer can actually read and execute. There are up to 40 instructions available. I've designed them on my own, and when I was designing them, I didn't really try to take them out of my head or something. I was just thinking, like, how can I do this or how can I do that? And that's the reason, and that's the way how I was actually adding new instructions. So once I needed a new feature, I just could add a new instruction. And once it get to 40 instructions, I really felt pretty satisfied, because literally all I wanted to do was now possible. And when the Chrome dinosaur was actually jumping here on this LCD screen, this was really fun thing to consider. So I thought that's kind of good enough to it's good enough to stop adding new instructions, basically, because I really wanted this sort of a thing to be minimalist. Well, anyway, now without further ado, let's actually start developing our hello world. So I start by clicking the start simulation button, and we're going to be inputting the machine codes here to the serial port and sending them to the CMK computer, running and see how it works. And we're going to be developing in the just the bare text editor, nothing special. And I'm going to be using this assembler.py Python script in order to assemble mnemonics to machine codes, in order to assemble this assembly to machine codes. And well, obviously we need to have Python 3 being installed in order to be able to kind of like assembling the code. And again, like a cheat sheet that I've provided, sort of a documentation for CMK computers. So all the instructions available can be found on the GitHub repo for the CMK computer. So here are all the instructions with the opcodes and assembly instructions, arguments, if available, only one argument, just like in good old 6502 processor. So this instruction set is really inspired by the 6502 processor, by the way, and the description for every single given instruction. So without further ado, let's actually start writing some code. So I recommend starting the code by the start label. It's not obvious, it's not essential, it's going to be working without that as well, but I just like doing like that, and that's just my preferred way of doing things. And the very first thing I want to do is to reset A and B registers. So from the previous video, you already know that there are two registers, A and B. There is a program counter, a stack pointer, and a zero flag. That's pretty much all about the CPU architecture. It's that simple. And well, even though CPU starts with A and B registers being set to 0 anyway, still it's a good practice to set them manually every time this kind of like the first instruction to spend, the first instructions to actually set these A and B register being equal to 0, to literally to reset them. Because if you're gonna be running this on the CMK computer several times in a row, in this case, once your program has finished its execution, the values of A and B register might be not equal to 0, and it's just not going to be working the next time. So in order to avoid that kind of scenario, we really need to make sure that we reset everything and set everything at program start, because the only thing that would get reset automatically is the program counter. So once it encounters the 0 terminated by, the program counter would be set back to 0. So the next time you run the program, it would be like the first instruction to execute would be this one that will provide just right in a moment. So the very first thing to consider, I want to say LDI 0x00. So it supports only 16 on the hexadecimal numbering system, and LDI stands for load immediate data to the A register. So here what we do, we literally want to reset the A register, and then there is no command to reset B register directly, but we can transfer the data from the A register to B, and hence the command TAB, which stands for transfer A to B. And this is the 1-byte instruction. So here we literally reset B register. So after these two lines, both A and B register would be equal to 0. And just to give you an idea that this is really the case, we have a nice DBG instruction, which would be printed to the serial port, the internal state of our CPU, so we can easily see what are the values of the registers after certain operations. And in order to get into the error, let's provide the exit label, and here I just say byte and 00. So byte is not an instruction, it just tells the assembler to assign to set the next byte equals to 0. And here we have just terminate program, or program terminates here. Let's say program terminates here. All right, and this is already enough to actually compile and run it. So if I just open the terminal in the current working directory, I'll probably already have one. Okay, and now assuming that we are in the directory where the assembler.py file is available, we can say python 3 assembler.py, and so I call the file test.asm because I already have hello.asm as the bundled thing. So here we just have a custom file. This file is called test.asm, and I just say test.asm. And now it just tells me the labels that I've used, the addresses of those labels, and the program bytes are here. Also, the program length is here. If you exceed the 512 bytes, it just won't let you exceed that value, because the maximum number of bytes you can send via serial port is 512, and if you're typing this via keypad, you can add more. But yeah, that's gonna be a bit of a pain. So we now can grab these bytes, and now we go to the simulator, and let's put the simulator here, and here fffd to a command to load bytes. So CMK computer is waiting for income data, paste this in, send, and notice that we're sending the bytes as encoded as the ASCII characters, and they do get decoded on the CMK computer. And now by simply typing ffff, we can run our program, and nothing happens on the display because we didn't yet do anything really, but it prints the debugging information, which is exactly the behavior of the dbg command. So we have the register A being set to 0, the register B being set to 0, the program counter is 4, and the stack pointer points to the very last address of 1K memory, and the 0 flag is equal to 1, which is true, by the way, because the A register has been set to 0, and this happens every time when the A register gets the value of 0. Okay, so now we need to define, now we need to store the data for the hello world string itself. So let's just say hello world like this, and here we need to define the bytes, the ASCII characters, the bytes representing the ASCII characters of the hello world string. I try to keep things simple so it doesn't load doing things like this, right? So we need to, as far as this project is really made for didactic purposes, so you need to do everything manually by hand. So you need to define byte by byte all the string, and then the custom 0 terminating character, you can use whatever character you want basically. And now let's go and find some online ASCII table here, and here we're going to be using the hexadecimal values for the hello world. So starting with H, and in hex this is 48, so I'm using that. So just define byte 48, then byte, just can make lots of bytes here. All right, so HE is 65, so 0x65. Now L, it takes time, yeah, but it's very didactic. So HAEL, where is the L? 6C twice, 0x6c, 0x6c. So I'm just defining the bytes for hello world string here, and meanwhile we can do the commentaries here. So this is the H, this is the H, this is E, this is E, this is L, this is L as well. All right, so now O, 6F, 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 and this is O, hello. Now the next one should be comma. So where is the comma? 2C, okay, 2C, and this is the comma. Right now I know by heart that space is hexadecimal 20 or decimal 32, and now world 77. Now O is 6F, okay, 6F, and this is O, sorry, not 0, O, R, 72, 72, what have I done? R, and L is 6C, 6C, and D is 64, 0x64, and this is D, and the exclamation mark is 0x21 if I'm not mistaken. That should be the case. And then we have a zero terminating character. So it might be a zero terminating character, or for instance, we can use some custom one like this. So this would be the byte we're going to be comparing the value at the A register during the loop in order to verify the fact that we have exhausted, we have looped over all the bytes within the string. So that's kind of the major idea behind it. And so here, just say that this is the string terminating character, and it can be whatever, right? And now the main loop, so let's call it like print loop basically, right? And here the instruction that we're going to be using in order to load the value of each of these bytes one by one to the A register is the instruction LDA. And let's have a look what it does. So it loads the data from memory address with the register B offset to A register. Now, how this works, this is one of the most essential things why it's worth actually watching this Hello World tutorial. So if I say LDA and Hello World like this, it would this Hello World would be replaced by the address of the Hello World label. Now let me just demonstrate how this is going to be working. So Hello World has an address of 0x0007. Now to this value, whatever we have in the B register would be added to this value, and hence the byte that we're going to be reading from the memory would get reference from that exact address. So here we can say like, so this is memory memory indexed by the Hello World. I would say, so if we're talking plus B register. So if we're talking like from the high level languages perspective. So this Hello World, where to start from, and plus the B register. But the better way, well, this, like if we're seeing this like from the index perspective, but from the pointers perspective, it's better to say like memory plus B register like this, and the value at memory plus B register. So as far as B register is equal to 0, the first byte to read would be this one. And then while we're going to be incrementing the B register, we're going to be respectively reading this one, and so on. So generally we can say like read next character in hello world string, right? And now inc stands for increment, and increments the value at the B register. So let me just quickly find that one. Yeah, increment value in B register, right? So after this instruction occurs, the value of B register is going to be 1, not 0, but 1, right? And then we want to loop back to our print loop. So I'm using the command that is called LPC, which stands for load program counter, and literally this is just an unconditional jump. So LPC print loop. Okay, and here we want to repeat print loop. Okay, but now it's kind of all fine, a part of the only thing, the problem here is that it's going to be an infinite loop, and it's not really that great. So we need a condition of when we can escape from this loop. And now here is where the string terminating character byte comes onto the stage. So once the value in the B register would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I guess. Maybe I just counted wrong. So the value at A register would be FE. So once we have the FE at A register, it tells us that we no longer need to actually read this string, and we can actually jump to this exit and terminate the program execution. So we can simply say compare 0x FE, so just a constant. So here we want to compare current byte, current character, let's say character in A register with 0x FE terminating character. Okay, and if it is if it equals, if the value of A register equals to FE, then the 0 flag is going to get set. So here we use the conditional jump. So this JMP stands for conditional jump. So here we want to jump to exit. So I can say if so, then jump to exit label, right? Jump to exit label, and that's pretty much all about it. And also we can here we can just print some debugging information. So we're not outputting anything to the screen yet, but just printing the debugging information. So we need to make sure that the A register would be getting the values of 40, 48, 65, 6C up to here, and the B register gets incremented after this instruction, and eventually the program shouldn't stuck in the infinite loop. So let's see if it actually works. So I'm compile the entire program, copy the bytes, and go into CMK computer. Well, I prefer hardware reset every time, so we can clear the serial monitor here, and FFFD to load the program. Now paste, send, wait a little bit. So on the real hardware it works really faster. It's like instantly gets loaded instantly. And FFFF, and now it should print several and here we go. So first we have register A equals to 0, register B equals to 0, then register A equals to 48. Because of the location of the debug instruction, we don't see the update of the B or the B flag. But anyway, it goes to it goes until hold on a sec. Where is A77, 6F, 6C, 21, 21, yeah, and then it drops. So the last value we have in A register is 21, and the B register is equal to C. Oh my god, A10, B11, C12. Yeah, so and register B is 12, right? So 21 is the exclamation mark. And as far as we jump in before bringing this debugging information, we actually don't see that register A contains this FE. So if we put the debug statement, for instance, here, like dbg here, then we will actually see that. But that's self-explanatory, so I'm not going to be demonstrating that as well. So now we know that as far as A register contains exactly the value of the next byte to print, what we can actually do, we can simply output this character to LCD screen. So here I can simply say output character to LCD screen, and here we want to increment the value of B register by 1 to increase the memory offset for LDA instruction. And by the way, the STA instruction works similarly to LDA, but what it does, it stores the value that is available in the A register to the memory plus the B register as an offset. So this kind of trick works for both reading and writing bytes from or to the memory. Okay, so currently it already should actually print hello world. So let's have a look if it works. So just exactly the same steps here. So let's reset the computer, clear the serial monitor, and FFFD to load the bytes, paste, send, and to run, I say FFFF command, and we got our hello world. Well, I had the debug somewhere, so I need to get rid of that. But anyway, we got the hello world, which is nice. Now, let's add a little bit of bells and whistles here. So yeah, we don't need this debug here anymore. And just to make it a bit more cute, we can add the delay. So let's say delay 0x, I don't know how many, let's say FF. So this would be 255 milliseconds delay, right? So just to make it like HELLO, comma, space, and so on. So just more eye-pleasing sort of a thing, all right? So let's try this as well. So we no longer need to print any debugging information. So, okay. And here we go. Yeah, it's really, you know, me personally, when I write some software for this computer, I really use the real hardware because it's easier to, it's really faster to develop in that way. But yeah, I don't have a good camera to film this. So, and again, like you would most likely would be using this online emulator. So that's the reason why I'm doing the tutorial. Well, that's the reason why during the tutorial I'm using this online emulator as well. And I would say like it prints like word, like letter by letter. And now the very last thing that you most likely would expect from the Hello World tutorial is just to print the new line. Or here we can actually print the new line, but we can move the cursor to the next. Just right over in here, and there is a pause instruction which assumes that A register holds the column to put the cursor to, and the B register holds the row to put the cursor to. So once we have initialized the A and B registers to the proper values, we can then call pause, and we'll have our cursor been placed exactly where we expect. So let's say LDI, so the row would be row 1, so I say LDI 0x01 and tap. So here what we do, I load 1 to register A and transfer it and transfer it to B register. This is the cursor column value, right? And then LDI 0x00, and this just loads 0 to a register, and this is the cursor, sorry, not the column, so this is the cursor row, and this is the cursor column value. And then I can simply say pause, and here we just set cursor at column, let's say at row 2 and column 1, right? So if we compile the code and copy and just let's reset things, so now it should be exactly the same, but the cursor would be placed here. So let's try to load the program. Okay, and send. All right, F, and let's have a look. So now I should place the cursor right over in here after the program ends, and it does. So this is it, guys. So we've just created a Hello World program for CMK computer. We did put the cursor to the new line, so the real classics here. And in the next tutorial, I think we can cover user-defined graphics, which is one of the most fascinating and exciting things in this computer, because LCD Shield can be, LCD screen and LCD Shield as well can be programmed to have up to 7, or from 0 to 7, I guess up to 8, yeah, user-defined characters. So instead of this these characters that you already have there, you can create your own characters, which is really fantastic thing, and that allows you to actually use them as the sprites in the games. And if you have a look at my Chrome Dino port to this computer, you'll see what am I talking about in particular. So in the next video, we'll have a look how to create a user-defined graphics for CodeMonkey Games computer, and this is it from my side. So thanks for watching, until the next time, and take care.